Okay. Greg, thank you for passing on to me, and Frank, thanks for the talk. So I'm going to talk about the wall of wind facility, which is also part of the NHERI network. So this is just a picture of the fans from the intake side. We have a 12 fan system, as you can see, very large systems to create the wind simulations. Um, you can look at wall of wind as an open jet large wind tunnel. And the cross-sectional area for testing is about 20 feet by 14 feet. So we can accommodate kind of large models and sometimes full-scale versions of subsystems or components. So we can do both large-scale and full-scale testing. We have a wind speed range of 10 to 157 miles per hour. And we wanted to achieve the 157 because that marks the category 5 hurricane wind based on the Saffir-Simpson scale. We can do various atmospheric boundary layer generation using our flow management system. We also have a turntable, 16 feet diameter, which can test models for various wind directions. So as I said, like it's a large wind tunnel. So many questions could be like, okay, what is the difference from a conventional wind tunnel that we have all seen? So these are some unique features and testing capabilities for the wall of wind, or we can call these the key strengths. So as I already mentioned, we can simulate up to category 5 hurricane winds, which is at the high end. We can do various different scales of testing, like we can do full scale, large scale, or even small scale. So those are the advantages that you can test various scale effects on a single model. And we have done that in the past using balconies, and we modeled it at a 1 to 180 case, then a 1 to 67 and 1 to 25, and we look at the scaling effects. We can also do destructive testing. That means we can increase the wind speed at certain increments, and we can see at what wind speed we see progressive failures of components. That's what we call destructive testing. So you can learn about the failure modes, and once you know the failure modes, you might go back to your drawing board and change your design. Also, it is good for checking retrofitting techniques, like we can test full-scale retrofitting strategies or mitigation strategies that you may have and test side by side one building without the mitigation technique and one building with the mitigation technique to see the difference or the performance of the mitigation. We can do wind-driven rain simulations because a lot of damage or losses happens because of the wind-driven rain in a hurricane, even at low wind speed. So even category 1 or 2 hurricanes are capable of doing a lot of losses because of the rain intrusion. So we can study all of that at the wall of wind. And we are just not focused on buildings. We can do other things like bridges or renewable energy system or lifeline infrastructure like power lines or communication towers or transmission towers and things like that. Okay. I think you're going to get a little more insight about the wall of wind when we do the virtual tour, but this is a general layout. So as you can see here, we have the operation control center from where we run the fans. It's called the control room here. And we send all the signals. We also can do the data acquisition from here. Then we have a flow management system, which are the bottom pictures. You can see also the turntable with roughness elements to simulate the atmospheric boundary layer. And on the right bottom, you have the staging area so that, let's say, if you want to build something in the wall of wind facility or instrument something before the testing, you can use that area. So large scale models can be fabricated, it can be built, it can be instrumented, and all of that in the staging area. And then you bring it on the turntable using forklift or other methods and test it at the wall of wind. So these are the resources that we have. We have a great team here. We have on one side, on the left-hand side, we have all the faculty. And I'd like to also mention that Dr. S.J. Lee, who has recently joined the Wall of Wind team, is an associate professor, and he would be the person who is kind of the liaison between the SimCenter and the Wall of Wind, because he has a lot of experience on numerical and computational approaches. So you're going to listen to his talk in this presentation as in this workshop as well. Other than that, we have our site operations manager, and we have staff who are very expert on wind engineering activities. And we also have educational person, Director of Education and Outreach, Mr. Eric Sala, who helps with the educational activities and connect or integrate the research with education. And we are going to talk about it later on. So we have a very vibrant team, and we are all here, Jonas, Amal, myself, Dr. Arwen, and the rest of the team to help you. This is a new capability that Amal is going to talk tomorrow or today about, probably tomorrow. So what you are seeing is a downburst simulation. So it's a non-synoptic wind simulation that you are seeing here. So we used to do only ABL kind of simulation. That means atmospheric boundary layer, which is kind of generally known as straight winds. Though nothing is straight, even in hurricanes, but it's generally considered as straight winds. But what you see here is a downburst that develops from thunderstorms, and it's non-synoptic and non-stationary. And this is the small scale version that kind of shows how a vortex is kind of developed, as you can see, and this will be replicated with the full scale wall of wind. So you're going to have an opportunity to compare what are the wind effects on a structure for synoptic kind of winds as well as non-synoptic. So this will be an addition on which Amal is going to give you more details. There is also another Cross-Awardee capabilities that we are developing with Lehigh, and this is on real-time hybrid simulation where we have subsystems. So we have a system that is experimental at the wall of wind, and then we have a numerical model residing at Lehigh in an experimental facility. And you can test various things here. You can test the effect of certain dampers on wind mitigation. We are right now doing a 40-story building on top of which there is a communication tower, which is Aeroelastic. So you can use this kind of capability to study the interaction between a flexible communication tower atop a very tall building. And these are some simulations, pictures, and Amal is going to again talk about this tomorrow. So what is the NHERI vision? If we look at the NHERI vision, then you're going to see we want to enable frontier research and education to do 4 things, very clear, okay? One is, how do we predict life cycle performance of civil infrastructure under hazards? That's the first thing. Then we have to reduce the reliance on physical testing through more numerical and computational modeling. That's one of the big thrust by NSF. And that's where the SimCenter also comes in, okay? Then it's not only about understanding the performance or doing computational modeling, but final goal is to come up with a new design or mitigation kind of approaches. So how do these research translate into innovative mitigation strategies and technologies? Okay, and lastly, how do we integrate research, education, and outreach to train an inclusive STEM workforce? And that could be students, that could be teachers, but people who are engaged with STEM, we want to develop that. So one of the capability, let's say about, I'm going to go through one by one these 4 things that we start with the life cycle performance. So to do life cycle performance, these are kind of tests that we do. So it's a full scale testing. As you can see, vibrations of a roofing system. This is a metal roofing under wind. And you can see we are seeing connection failures at various parts of this system. So because of the capability that we have to do large scale or full scale testing, we can understand the performance of the system or study the performance. And we can see that how can we learn about those performance and then come up with mitigation or retrofitting or new design techniques to improve their performance. So we have that capability. As you can see here on the picture, We are simulating this up to 159 miles per hour of wind speed, which is very high category 5 wind speed. As I mentioned to you that it's not only buildings, we are also interested in infrastructure. So this is another research about looking at traffic signals, and we are trying to capture aeroelastic and aerodynamic responses of traffic signals. So as you can see, the wind speed is slowly increasing. You're going to see that there is kind of an increase in the vibrations, and then it's almost like an instability that's setting in, which might cause a destruction or a failure. Okay, and so that's the system failed. So here at the wall of wind, you can do these kind of testing, which is not always feasible in a smaller wind tunnel. So you can look at the infrastructure performance at full scale, and you can measure the effects of the wind in terms of forces, moments, strains, accelerations, and things like that. We are adding a capability to the wall of wind, which I think will be unique to many of the users, and you're really going to use this for validating your numerical or computational model. This is called the particle image velocimetry. So what you do is you seed the experiment, or here you can see a bluff body. The flow is coming from right to the left, and there are a lot of particles that are inside the flow, which is introduced, and then we have laser sheets that are taking photos, and from these you can have correlation to understand the flow field beyond the structure or around the structure. So again, you can see like how the laser is working, and you can see there are like wake and vortices beyond the bluff body, and you can capture those, and from that you can come up with the fluid structure interaction. So this kind of capability is going to introduce a new niche in fundamental fluid mechanics area, and that can propel transdisciplinary research as well, while validating computational modeling. Then it comes to mitigation. So this is another technique that, an example on the left-hand side, you can see like there are vortices coming off on the corner of a roof, which creates suction and destruction of the roofing elements, like you can see the scouring of the gravels. And on the right hand side, you see a mitigation technique, which is wind turbines at the edge of the building, and it's disrupting the vortices. So that at the same time, you're reducing the wind loads as well, you're producing green energy. And we are right now collaborating with industry how to commercialize these kind of mitigations. So this is an example of where you can do side-by-side testing of one building with mitigation, another building without mitigation, and compare the performance of unique mitigation devices or retrofitting technologies. We do a lot of integration of research, education, and outreach. So on the left-hand side, you're going to see like these are teachers, high school teachers, who are at the wall of wind, building small wind tunnels. This is a summer RET program, research experience for teachers, where they come and learn about wind engineering, and then they take those lessons back to their classroom to influence the career path of their students. So they are interested in natural hazards engineering, and they join an engineering program. On the right hand side is the REU students, research experience for undergraduates. They come from various parts of the US at all the different NHERI facilities during the summer. And in our case, they work hand in hand with the teachers so that you can get a great integration of research, education, and outreach about how to propel the STEM workforce and make a very inclusive STEM workforce interested in natural hazards. Based on all the achievements that we have and the capabilities that we produce, the American Society of Civil Engineers has selected us as the winner of the 2018 Charles Pankow Award, because they think we are really doing something which is good to enhance the safety and resiliency of new and existing buildings. Now, as we start about how do we provide our support to the users, our site operations manager will have a good discussion tomorrow But this is a brief overview of what are the various supports. We are going to help you with specimen design, construction, instrumentation, test protocol, and software implementation. We are going to operate the wall of wind for your testing. We are going to help you with video recording and data acquisition. We are going to give you like safety trainings as needed. And we are also going to assist you with proposal development stage, because you need a lot of information on, okay, what kind of experiments are enabled by this facility. So Dr. Steve Diaz is going to talk more about this tomorrow. But we have a suite of support items that we are going to help you with about any proposal. So the last thing that I mentioned in there is NSF proposal support. So this is a linear progression of logic of how a competitive NSF proposal can be developed. And I'm going to talk about this tomorrow during the talk about how to develop competitive NSF proposals. But I just wanted to introduce that this is going to be the backbone of what I'm going to talk tomorrow. And then anyone can contact me if they're trying to develop some proposals, including career proposals, and I can try to help in whatever way I would be able to. This is a picture of the workshop. I know that we are all virtual right now, but this is what it is to look like pre-COVID. So hopefully with all the vaccines and things that are going to come up, we are going to go back to this kind of mode where we interact with our users and they come and they learn about the wall of wind. And it's a fantastic meeting that we have here. And this is a popular picture spot where we have the big yellow fans. With that, I'd like to thank NSF for their support. And that's the end of my presentation. And we are going to talk in more details about various items that I kind of alluded in my presentation. So Greg, back to you.
Okay. Actually, Arindam, before we move on, I noticed that a question did come through on chat, which is an interesting one. I'm not sure there's a clear answer to. I don't know if you could read that, or I could read it out to you and see if you have comment, or I think Hassan Kareem is on board as well. But the question is that the wall of wind generates for a very specific limited area. However, in real life, the radius of a hurricane is much wider than what you could generate in the wall of wind. So how would you compare them? I mean, I guess the point is, how do you relate things that you could study within the wind tunnel to the full-scale hurricane scenario?
Anyone wants to take that up? Giannis, Mal, Dr. Kareem, or?
As Greg said, the answer is not clear, but I don't know if Golam has an earthquake background, but I guess like what we're trying to do at the wall of wind is not replicate the whole like system that you see in nature. We have a limited test section, as you mentioned, and that is sufficient to test either like a smaller structure or a building component. And what we try to achieve there is to make sure that we do it scientifically and we simulate the right properties of natural wind during this kind of extreme wind for that particular test section that we utilize. So our research in wind engineering is testing a smaller building or a small scale building model or a building component, if you want, and generate the proper flow field in order to study the response of the model or the actual structural system that we're testing.
Can I add in? I just got the last end of the question.
Absolutely.
My impression is that we don't bring the hurricane to the wind tunnel. What we do is just like Greg and Tim, the inflow simulation, we try to bring the inflow conditions as close to as what is in the hurricane in the wind tunnel, and then do our experiments as opposed to the other conditions which are like for regular winds and stuff.
Yeah, and thank you both Giannis and Dr. Kareem. And I'd like to add, I think one of the things that acts in our advantage, I think, is the hurricane, as you mentioned, is way, way bigger, like it's huge. So if you compare the scale of a building to the real hurricane, the whole dimension of the hurricane, then really it sees a very local kind of flow based on where the building is located with respect to that hurricane. So we are not trying to develop the entire hurricane, but we are trying to develop what is the effect of the hurricane to that building based on its location. And then, of course, that's how we change the wind direction. So we can simulate wind coming from various directions and various flows as will be seen by the building as a hurricane passes through. So that's would be my addition to what Jonas and Dr. Corey mentioned.
Okay, well, maybe we should probably move on. I see another question came through. We'll keep track of that, maybe come back to that question. But maybe to stay a little bit on track, Arindam,
yes,
do you want
Greg,
to introduce?
Yeah, Amal will be presenting on Downburst, I think. So she will be able to answer this kind of question.
Yes.
Yeah.
Yes, tomorrow's presentation, Amal can handle this. So Amal, just take a note of this and then we'll come to that question.
Thank you, Elena. Thank you, Elena. Thanks.